Greetings. This video presentation is part of a series of lectures for the course cee235a Advanced Structural Analysis. I am Professor Arturo Tajiroglu of UCLA. The title of this presentation is Pure Bending of Beams with Symmetrical Cross-Sections, and this video presentation is meant to form a basis for more advanced topics such as the direct stiffness method, as well as bending of beams with non-symmetrical cross-sections and bending of beams under applied transverse shear forces. The basic beam theory that we're going to discuss, namely the Bernoulli-Euler beam theory, is going to be based upon certain assumptions of member geometry and deformations. The first of these assumptions is that the cross-sectional dimensions are small relative to the length of the beam, so that we're looking at a thin and slender body. So here in the graph, B and H denote some characteristic dimensions of the cross-section, which does not necessarily have to be rectangular, but is shown as a rectangle for the sake of argument here. We want those two dimensions to be much smaller than L, the length of the beam. Here, Y and Z denote the cross-sectional coordinate axes, and X is the axial coordinate of the beam. The second crucial assumption in formulating the Bernoulli-Euler beam theory is that the transverse deflections are small relative to the depth of the beam. So if we denote the transverse deflections of the beam in the Y and Z directions as U sub Y and U sub Z respectively, then we want both of those deflections under applied forces to be much smaller than the characteristic dimensions of the cross-section B and H. The most crucial ingredient of a beam theory, including the Bernoulli-Euler beam theory, is the kinematic hypothesis that it employs. In the Bernoulli-Euler beam theory, the kinematic hypothesis is quite simple. Plane sections remain plane. In other words, there's no warpage in the cross-section due to applied moments. So as illustrated in the graph that's shown here, if we apply a bending moment to a segment of a Bernoulli-Euler beam, the cross-section will only translate and rotate in space due to these applied forces, but it will not change its size or shape. So for example, if we have a rectangular cross-section prior to deformations, prior to the application of the moment, then after the application, this rectangular cross-section will remain a rectangle. In fact, it is going to be the same size rectangle, not a warped version of it, not a smaller version of it, not a larger version of it. It'll be an identical version of it that is merely translated and rotated in space. This kinematic hypothesis is due to 17th, 18th century mathematicians Jacob Bernoulli and Leonhard Euler, so it's simply called as the Bernoulli-Euler kinematic hypothesis. So once we have the kinematic hypothesis, we can evaluate the consequences of it. First of all, if the plane section remains a plane, then the longitudinal strain here, epsilon xx, must be varying linearly over the cross-section. So the topmost fiber must be under compression, the bottommost fiber must be under tension, and somewhere in between, therefore, there must be a fiber that is neither extended nor compressed. And if we connect up all the fibers that experience this for the entire beam, we obtain what we call the neutral surface, which is marked here by this orange dashed line. If we know the strain distribution, then it's easy also to determine the stress distribution using the linear elastic constitutive law. And in this particular case, all we have to do, because there are no other strains, is to multiply the strain distribution with just Young's modulus. That's going to give us the stress distribution. And in particular, therefore, we will expect the highest compressive stress to be at the top of the beam, denoted here as sigma max, and then the smallest, the most negative stress to be at the bottom of the beam, that will be sigma min, for example. So the other consequence of the kinematic hypothesis is that the transverse shear strains are small in comparison to the axial strains, and therefore they may be neglected. This implies that the cross-section does not get warped, obviously. So how does it appear to us geometrically? Imagine that we have painted plus marks on the side of our beam before deformation. And of course, these plus marks are going to have 90-degree angles at their intersections before the deformation. What Bernoulli-Euler kinematic hypothesis implies is that even after the deformation, these plus mark signs will retain their 90-degree angles. Of course, depending on their location, the horizontal arms of these plus marks may become shorter or longer. Those that will be obviously above the neutral plane are going to have shorter horizontal arms because they are being compressed, and those that are below the neutral plane will have longer horizontal arms because they are being stretched. But none of those plus marks, those hypothetical plus marks, whether they're above or below the neutral plane, anywhere else on the beam, they're not going to lose their 90-degree angles. So let us now take a, for example, closer look at this one, an elevation that is above the neutral plane marked with this dashed yellow line. So here the plus mark is going to still have a 90-degree angle after the forces, the moment has been applied, only that its horizontal arm is going to be a little bit shorter than the length that it originally had prior to the application of the moments. So from this qualitative or somewhat quantitative information, we should be able to obtain some relationships between stresses and strains as well as deformations of the beam. So let's take a closer look at the axial strain distribution. So here is the segment of a beam before the deformation. The neutral plane is marked with a dashed orange line. And I'm going to be taking a closer look at two segments that are separated, two cross sections that are separated by distance delta x along the length of the beam, such that the dashed vertical yellow line is at x, the left dashed vertical yellow line is at x away from the origin, and the one on the right is x plus delta x away from the origin. So I will put my coordinate axis at the neutral axis or the neutral plane of this cross section, and I do not yet know where this neutral plane is relative to, say, the bottom of the beam. And of course, to go along with my original title, I'm going to assume that this cross section has a plane of symmetry, and then the axis that defines that plane of symmetry is the y-axis in this particular case. So to develop my equations, I'm going to climb up a little bit higher in the positive y direction to a different elevation, which is marked by this horizontal dashed yellow line. And I'm going to mark the two line segments, MN and IJ, on this portion of the beam before the deformation. So let us now draw the deformed shape under applied pure bending moments for this little segment. So as you can see, I am still using the letters M and N for the deformed version of the segment, the red segment, which is the segment at the neutral plane. I'm doing this on purpose because if the red segment is indeed on the neutral plane, then its length will not have changed because those fibers are neither being compressed nor being extended. So it is going to retain its original length. The same is not true for I and J, however. That's why I marked it as I prime, J prime, that segment, this little purple segment, because its length will have changed. In fact, it should become shorter to satisfy the Bernoulli-Euler kinematic hypothesis. To make further progress, I'm going to extend the deformed cross-sectional lines above the beam. And since they're no longer parallel, they're going to intersect at a point. That point is referred to as the center of curvature for this little segment. And of course, if these two cross sections are separated by a small distance from each other, dx, then they're going to be sweeping a small angle, which I denoted here as d theta. So if I measure the distance from the center of curvature to the neutral plane of the beam, I'm going to obtain the so-called radius of curvature, which is denoted as rho. So for this little segment, it's obvious that if the radius of curvature is infinity, then I'm looking at a beam that is flat. And if the radius of curvature becomes 0, this means that I have created a perfect kink at the middle of this little segment, which of course is not practically possible. So with these definitions intact, we can just further define other quantities that we are going to end up using frequently. The first of these is the so-called curvature, which is simply 1 over the reciprocal of the radius of curvature. So it's going to have units of 1 over length, and it's simply 1 over rho. And the convention here in the classical theory is that the positive moment causes a positive curvature. So because the mz that I have marked here on the picture is a positive moment, because you're using a right-hand rule, and if you recall what that is, then this is a positive moment, then the beam will curve up, and this is a positive curvature. This is a mere convention, but this is the usual convention adopted by almost everybody. So now I know rho, and I want to obtain a measure of strain at the location elevation y of this little segment I prime j prime. So for that I need to determine the new length of the segment, subtract the original length of the segment, and normalize the result by the original segment. That is the definition of Lagrangian strain. So we know that both I prime and j prime are located rho minus y away from the center of curvature, so we've already also marked that. So epsilon xx, as I mentioned before, is merely a percentage, which is what is the length change over the original length. So the length change is the difference between I prime j prime and ij, and then the original length is ij itself. Of course, the original length ij is also equal to mn, so I can replace that with those. And then use a basic observation from trigonometry or geometry that the length of the arc, the circular arc, I prime j prime, is merely the radius that of the circle that arc belongs to, which is rho minus y, times the angle d theta. And of course, the same geometry argument can be made to relate the radius of curvature and the angle to mn, and that is going to be simply rho d theta. And of course, we know by definition that that distance has not changed after the deformation, that length segment. So this must mean that rho d theta is also at the same time equal to dx. So now we can make some substitutions of these facts into the equation above for epsilon xx, and merely observe that epsilon xx must be equal to minus y over rho, and at the same time, because 1 over rho is d theta dx from the second equation for mn below, that epsilon xx is equal to minus y times d theta dx. So let us make some observations here. When y is equal to 0, epsilon xx is 0, we are at the neutral plane. Of course, we do not yet know what that origin of y is relative to the cross-section itself. For example, we do not know how far it is from the bottom of the segment for this little trapezoid, for example, yet. We will discover that soon, but we know that when y is equal to 0, we are at the neutral plane. And epsilon xx varies linearly as dictated by the Bernoulli-Euler kinematic hypothesis with respect to y, so that when y is the largest in the cross-section, we're going to have the largest compressive strain, the largest negative strain, and when y is the smallest or largest in the negative distance, negative direction, then epsilon xx will be the largest tensile strain. The second observation we can make right here is that whatever this angle theta is, if we can differentiate that field with respect to x, we're also going to obtain epsilon xx after multiplying with minus y, that is. Okay, so now we have collected all this information. Let us try to deduce the stress distribution and also location of the neutral plane or the neutral axis relative to the dimensions of the shape of the cross section. So I've just reproduced the original formula from the previous page, and I've also added an alternative representation for epsilon xx, which is minus kappa times y, because if 1 over rho is just kappa of the curvature, then minus kappa times y must be epsilon xx. And let us look at a more generic cross-section that has a plane of symmetry. Let's say that we are looking at a T-shaped cross-section. And I have created a version of this cross-section after the deformation takes place. It is still a T. It is a same size T, and it is not a warped T. And of course, those fibers that are above the neutral plane are going to get the largest compressive strain, and those that are below will get the largest tensile strains. And of course, the neutral plane will be somewhere in between. We do not yet know where it is. Is it at very close to the top of the T section, very close to the bottom? Is it at the middle of it? We need to find that out. So here's a plan view of the cross section. We see the neutral plane. X is the axial coordinate that is coming towards us from the plane of the slide, and y and z are the cross-sectional coordinates. Since there are no other strain components acting on this deformable body, the linear elastic constitutive law will simply tell us that the axial stress, which is the only direct stress that appears in this mode of deformation, is simply the Young's modulus times the axial Lagrangian strain epsilon xx, and that is simply then minus e times y over rho, or equivalently minus e times y times d theta dx. So let us first ask the question, where does the neutral plane lie? To answer that, let us first inspect what the resultant axial force is. If this is a pure bending problem, then the resultant that is causing this deformation is merely a bending moment, and there are no other resultants in place. So there's no axial force, which means that if we integrated this stress distribution throughout the cross-section, it should be equal to 0. So here is that, sigma xx integrated over the entire cross-section, collectively denoted as gamma, and that resultant stress must be equal to 0. If we plug in the result that we've obtained through the constitutive law and the kinematic hypothesis into the integrand, and pull out all the constants that do not vary with respect to the cross-sectional coordinates y and z outside the integral, we obtain this little formula. So on the outside we have minus e over rho, none of which in a homogeneous beam will depend on y or z, which is what dA is. dA is simply dy times dz. And on the inside we just have an integral y dA, y. So if E, the Young's modulus, and the curvature are non-zero in general, the only way that this can always be equal to 0 is that the integral itself is equal to 0. And of course, from our simple prior knowledge of geometry, we know that if we want to obtain the value of this integral, y dA, which is the so-called first moment of area, we can also obtain it by multiplying the entire cross-sectional area with the moment arm for the cross-section, say y bar. So if the integral itself is equal to 0, and since we know that a is not equal to 0, this tells us that y bar must be equal to 0. So where we have put the neutral plane is indeed the moment arm for the cross-sectional area, and then because this y bar is equal to 0, and this must be therefore the centroid of the cross-section. So from the fact that the axial resultant force is equal to 0, we have deduced the fact that the neutral plane must be at the centroid of the cross-section, because there's no other point that will satisfy this integral being equal to 0 unless we have put the origin of our coordinate system at the centroid itself. So now we have discovered a fundamental fact about where the neutral plane is. it's at the centroid of the cross-section, which means it does not really depend upon the applied moments. Whatever moment we apply, the neutral plane is not a property of it, but it only is a property of the cross-sectional shape and dimensions. So that being discovered, we can go back to our stress and obtain its relationship with the moment that caused it. Of course, if we have the stress distribution, all we need to do to compute the moment that caused it is to evaluate the integral of the stress field multiplied by the moment arm y. If we look at a small segment highlighted as dA in here in the cross section, we need to find the force that is acting through that little area segment, and that is merely sigma xx times dA. And then we need to multiply that force with the moment arm from the neutral plane, and then we need to integrate all that result across the entire cross section. That should give us the moment mz. And of course, if we have denoted the positive moment to create a compressive stress at the and compressive strains at the top above the neutral plane, then we have to fix the signs. We need to put a minus sign at the top. But just inspect this integral and observe that its signs are consistent. So once we have put in the formula for sigma xx that we have obtained previously into this integral and plug in minus y times e over rho into the integrand, and pull out all the terms that are not functions of dy and dz, we obtain the rightmost result, that mz must be equal to e over rho times the y squared, integral of y squared over the cross section. So this particular quantity is called the second moment of area, and in this particular case it is the second moment of area about the z-axis. And in multi-axial bending, we'd be interested in computing another second moment of area about the y-axis, for example, but that's the subject matter for a different lecture. Another name that we used to denote this, to refer to this quantity, is also the planar moment of inertia, and in this case about the z-axis. So what we have so far is a relationship between a measure of deformation, which is 1 over what 1 over rho is, or rho is the radius of curvature or curvature itself, and the applied moment. And the quantity, the constant that relates the two to each other, is the EI-ZZ term here. And this product is often referred to as the bending stiffness, and in this particular case it is the bending stiffness about the z-axis. So if we read this expression that we have obtained in words, we would read it as follows. We would say that the bending moment is equal to 1 over the radius of curvature times the bending stiffness, or equivalently, the bending moment is equal to curvature times the bending stiffness. So it's we have obtained a constitutive relationship that relates a measure of deformation, i.e. curvature, to a measure of forces or stresses, in this case the resultant moment. And the constitutive material coefficient here is EI. And unlike the material point constitutive relationship, which only has material properties, Young's modulus, Poisson's ratio, we have some geometric quantity seeping in due to the kinematic hypothesis that we have adopted. We can re-express this quantity, this formula, slightly differently by plugging in an expression from the box, the purple box on the left, for 1 over rho. So from the purple box on the left, we see that 1 over rho is simply sigma divided by minus EY. And if we make that substitution in the expression on the right, we obtain sigma xx is equal to minus mz over izz times y. This formula is usually referred to as the flexure formula, and it tells us how the moment is related to the stress, as well as how the stress varies within the cross section. So let's inspect this a little bit. When y is equal to 0, i.e. when we are at the neutral plane or the neutral axis, the axial stress is 0 because those fibers are neither stretching nor becoming shorter. And at the largest distances from the neutral plane that we can find for y, the topmost and the bottommost fibers, we're going to be having the largest compressive and tensile stresses. So when y is obtains or attains its most positive value, then sigma will attain its most negative value. In other words, it's going to reach its most compressive value within the cross section, and vice versa for the bottommost fiber. Again, we have a relationship that tells us how the deformation varies with respect to applied moment, and that is simply 1 over the radius of curvature rho, or in other words, curvature is equal to moment divided by the bending stiffness. Now that we have obtained these consequences of the Bernoulli-Euler kinematic hypothesis, let us just apply it to some cross sections. And first I will give you a recipe for this application, and then I'm going to give you a specific example. In order to apply the flexure formula to a given cross section, the first thing we need to do is to locate the centroid of the cross section, and for that we need to obtain, or we may have to evaluate the first moments of area, etc. And in the example that I'll give you next, you'll clearly see how that works out. But once we have located the centroid of the cross section, we know now where the neutral plane is, and we know now where to put our cross-sectional origin for the y and z axes. So after that, we need to obtain the second moment of area of this entire cross-section about the z-axis. So we need to calculate the planar moment of inertia IZZ. Sometimes we can do this in closed form for a given cross-section, and sometimes we can take a shortcut and use the so-called parallel axis theorem to obtain the second moment of area for the cross-section. The second moment of area of a given cross-section can be computed by obtaining the second moment of area of simpler segments, such as rectangular segments of the cross-section relative to their own origins or centroids, and adding to them, which are denoted here as I sub ZZ OI, and adding to them the distance from their centroids to the centroid of the entire cross-section, DI squared, times their cross-sectional areas. I am not going to offer you a proof of this, but you can just look it up. It's a simple theorem that you can utilize to simply calculate the second moment of area of a cross-section that you can break up into simpler ones. So here I have broken up this T section into 2 rectangles, and it's really easy to determine the centroid of these rectangles. They'll be just in the middle of the rectangle. Then I will have to determine the distance of those centroids, which are marked by the pink and blue circles, to the centroid of the entire cross section. So they'll be D1 for section 1 and D2 for section 2. And to apply the parallel axis theorem, all I need to do is just multiply, for example, A1 with D1 squared, and add to that the second moment of area of section 1 with respect to its own centroidal axis, and repeat the process for section 2. Once I've done all my calculations and additions, I will have obtained IZZ. Then I can apply the flexure formula with the knowledge of MZ, so that if somebody gives me my MZ, the applied MZ, then I can determine the stress distribution of the entire cross section, the maximum and minimum stresses, etc. And of course, in all these calculations, I better remember that the positive moment causes a compression in the material fibers above the neutral plane, and that it causes tension in the material below the neutral plane. Let us solve now a specific example with dimensions. So here I'm looking at a T-section. The flange of the T-section has a 1-inch thickness, and the web of the T-section is 5 inches long, and the other dimensions are given. The first thing I need to do is to determine where the centroid is. To do that, I'm going to create a temporary axis, let's call it eta, that runs from the bottom of the T-section towards the top in the same direction as y, such that when eta is equal to 0, I'm at the bottom of the t section. So the unknown distance that I have from this origin, this new origin of eta, I'm going to mark it simply as eta bar. So my question then is, what is eta bar? How far is the centroid of the t section from the bottom of the t section itself? If I'm making measurements of the first moment of area with my new coordinate system eta that has an origin at the bottom of the t section, then the first moment of area is simply the integral of eta times dA over the entire cross section. And I can break up this integral into two parts, an integral over the web of the cross section and an integral of the flange over the flange of the cross section. Let's say that the flange is denoted as A1 and the web is denoted as A2. So this means that I can compute their first moments of area relative to the bottom of the t section by multiplying the distance of their centroids from the bottom, which are denoted as eta 1 bar and eta 2 bar, with their areas, which are denoted as A1 and A2. And this sum total must be equal to the total area multiplied by none other than eta bar, which is what I'm trying to find. So let us calculate the right-hand side of this equation. Eta 1 bar is simply the distance of the centroid of the flange of the t section from the bottom, which is going to be 5 inches plus a half. And A1 will be the area of the flange, which is 1 inch times 5 inches. That's 5 inches squared. And to that, I'm going to add eta 2 bar times A2. And eta 2 bar is the distance of the web of the t section, centroid from the bottom. That is going to be half of 5 inches, which is 2.5 inches. And A2 will be simply 5 times 1 inch, 5 inches squared. If I add all those numbers up, I get 40 inches cubed, which is what the unit of the first moment of area is. And if I divide this result by the entire cross-sectional area, which is 10 inches squared, then I will have found that eta bar is merely 4 inches. So eta bar, the centroid of the cross-section, is 4 inches from the bottom of the t section. Now that we know where the origin is located, we can then determine the second moment of area relative to this z-axis. And I'm going to be using the parallel axis theorem, and I'll chop up again my cross-section into two parts, the flange and the web, and use the formula to compute the terms using the parallel axis theorem. So let's take a look at the flange first, the top segment, the horizontal segment of the t section. So for that, I will need first the second moment of area of that section relative to its own original own centroid, and that formula is simply the bottom length 5 times the height cubed, which is 1 cubed, divided by 12. That is a formula that you can derive by yourself for rectangular cross sections. And then to that, I will add the cross-sectional area of the flange, which is 5 times 1, and then the distance of the centroid of the flange to the centroid of the entire section. The centroid of the flange is located obviously 1.5 inches from the centroid of the entire cross-section. You can compute that with the knowledge of eta bar being 4 inches. Because if you subtract from 5 inches the height of the web, the 4 inches, you'll get 1 inch, and then a ½ inch for the thickness of the flange will get you the 1.5 inches you're looking for. You can repeat the process for the web itself, and you're going to obtain those numbers, and if you add them all up, you find out that the IZZ for the entire cross-section is 33.3 inches to the fourth, and the units are here correct. It's length to the power 4 is the correct unit for a second moment of area. Now that we know IZZ, we can obtain, or we can utilize the formula and obtain any kind of stress value at any height or at any elevation along the length of the cross section. Now you might be wondering why we kept talking about pure bending. Because first of all, it is a simpler case to discuss, but it is also a relatively difficult case to realize in practice. Pure bending does not really occur unless we actually force it to occur. Usually bending is caused by forces applied transversely, and when you have transverse forces, you have transverse shear, and therefore transverse shear is always coupled with the moment. It is very difficult to see actually a pure bending case in real life. However, in a laboratory setting, we can achieve this. We can achieve a pure bending state where a segment of the beam is under pure bending with no applied internal shear forces. Case in point, here's a so-called 4-point bending test, where a simply supported beam is subject to equal vertical loads of magnitude P. If we look at the shear diagram for this beam, the shear force diagram, we see that the reactions will be vertical and will have equal magnitudes of P. And when you move from point A to point B, you're going to have a constant shear force. But at point B, that shear force will become zero, and zero shear force will continue all the way up to point C. And again, then you'll see the reverse of the case, and you're going to get a segment with shear force. However, note that the middle segment marked by points B and C is free of shear forces. And if you look at the moment diagram, you see that simply the moment in that segment is constant, and in this particular case it's going to have a magnitude of PL. So this middle segment of this 4-point bending case is going to be subject to pure bending. There won't be any shear forces there. And as I was telling you earlier, usually bending moment is accompanied by shear, and you see that the leftmost segment and the rightmost segment here are precisely like that, where there is shear and at the same time there's moment. And those two quantities are coupled with each other, and we will see the consequences of this coupling next when we start discussing the transverse deflections in beams. So let's move on to that topic. Let's assume, for the sake of argument, we are looking at a cantilever beam, and this is the undeformed version of that cantilever beam. And if we apply some transverse forces and moments, it bends and it deforms into this shape. So I'm going to be measuring the transverse vertical deflections of this beam. I'm going to denote them as V. And of course, the vertical deflections may vary along the length of the beam. So V in general is a field. It's a variable. It's a function of x. So if at position x the value of the transverse deflection is Vx, then a little distance away from this position along the axial length of the beam, I'm going to be encountering in general a different deflection, which I denote here as V at x plus delta x. What I'm going to do is I'm going to connect those 2 points on the neutral plane, which is what I'm drawing here. I'm not drawing the entire cross-section of the beam, I'm just drawing the neutral plane of it. And it is okay for me to do that, because if I know what the neutral plane is doing, then at the same time, therefore, I know what the entire beam is doing, because plane sections remain plane. So all I need to do in looking at the transverse deflections of beams is really to take a look at what the neutral axis of those beams are doing. So I'm going to connect the 2 points with each other with a secant chord, this thick pink line, and I'm going to try and measure the angle that connects the 2 line segments in the limit as I shrink delta x towards the x position. I can do that by simply evaluating the ratio of the difference between V at x plus delta x and Vx and delta x itself. That is now going to give me an angle, or a tangent of the angle that for that secant chord. And as I take the limit as delta x goes to 0, I'll be converging the tangent line for the neutral plane, which I denoted here as theta. We know from calculus that this limit is nothing other than the first derivative of the transverse deflection field V with respect to x which we sometimes also denote as V prime. So if we somehow can obtain V and differentiate that with respect to x, what we obtain is the angle theta that the neutral plane makes, neutral plane's tangent makes with the horizontal direction x. It is not a coincidence that I'm labeling this angle theta because we have seen the same angle before when we were defining the radius and the center of curvature. Remember that the angle that we have swept across a circle when we were moving from one point of the beam to another point which was separated by a distance delta x, that angle was d theta. Well, it is the same angle as this angle theta. It's rather an increment of it, and you can see this from the simple geometry that if the angle that the horizontal, if the neutral plane's tangent makes with the horizontal direction is theta on the left end of the segment, then if you sweep a d theta segment at the center of curvature, then the same angle will have been incremented by an identical increment d theta. Hence, it's appropriate to use the same name for those two angles. So, of course, again, from this picture, therefore, we can also write the fact that rho times d theta is equal to dx, because after all, we're on the neutral plane, and the neutral plane did not change its length. We can rewrite that expression slightly differently. D theta dx is equal to 1 over rho. And because theta itself is equal to the first derivative of v, this means that the second derivative of v with respect to x, in other words, v double prime, will be equal to 1 over rho, or the curvature. So if we want to obtain theta, we need to differentiate v once. And if we want to obtain curvature, or 1 over the radius of curvature, we need to differentiate v twice. Armed with this knowledge, now we can go ahead and determine what will happen to beams that are loaded with transverse loads and shear and moments, and what kind of deflections that they will incur from that. The first thing we need to do is to obtain equilibrium equations. For that, I have cut out a segment of a beam, and I've written the most general expression that I can write for this little segment while obeying the sign convention that I introduced earlier. So on the left end of the beam, which is located at x away from the origin, the resultant moment, the internal moment, is mz. The positive direction is clockwise. The resultant shear force is Vy. The positive direction is downwards. And on the right end of the beam, which is located at x plus delta x away from the origin, these quantities may have changed and attain new values. I generically wrote down as Vy plus dVy and Mz plus dMz. And this change is due to an external agent, which is generically written as Py, the transverse load in the y direction of x, because it can also change with x. Once we have this picture, we can write down the balance of moment and the balance of forces in the for this little segment. These are simply dmz dx plus vy is equal to 0, and dvy dx plus py is equal to 0. These are the two equations we have. The first one is the moment equilibrium. The second one is the force equilibrium in the y direction. Now I'm going to take these two equilibrium equations and express them ultimately with respect to the transverse deflection field. So I'm going to be writing up an equilibrium expression using the displacement field as the primary variable. In order to do that, I'm going to have to bring in the strains and the displacements into the picture. So for that, the first thing I'm going to recall is the relationship between the curvature and the transverse deflection V. So the second derivative of the transverse deflection was merely equal to the curvature. I'll refer to that as the strain displacement equation, which is something that is more appropriate for continuum definitions of strains and displacements. In this case, it's a resultant-based definition, but nonetheless it is equivalent. I'm relating curvature to a deflection, displacement v. I will also bring in a constitutive relationship. In this particular case, it's going to be the relationship between the moment and the curvature, and it's simply moment is equal to bending stiffness times the curvature. I'll take these two equations in the boxes, the blue and the yellow box, and weave them into the equations on the left. To do that, first I'm going to condense out one of the equations in favor of the other on the left side. To do that, I will differentiate the equation at the top for the moment equilibrium once with respect to x. So on the left hand side, I'm going to get the derivative of moment plus the derivative of the shear force. And on the right hand side, I'm going to differentiate 0, which is a constant with respect to x, which will remain a 0. Once I have done that, I can then go ahead and plug in the expression for the derivative of Vy with respect to x into the second equation, which is going to be merely introducing a minus sign into that equation, so that the derivative of moment minus py is equal to 0. So the second equation that I'm writing there is balance of forces in the y direction, except now it's written as a function of moment. So now if we evaluate this derivative, we see that the second derivative of moment is equal to the transverse load at any location along the length of the beam x. From the expressions on the right hand side, we see obviously that the bending moment mz is equal to the bending stiffness EIZZ times the second derivative of the transverse displacements, and we can take this expression for a moment and plug it into the force equilibrium expression that we have just derived to obtain this expression, that the second derivative of the bending stiffness times the second derivative of transverse displacement is equal to py. For prismatic beams, the Young's modulus and the second moment of area will not be functions of x, so we can take them outside the derivative and obtain this simple expression. It says the bending stiffness times the fourth derivative of the transverse deflection with respect to the axial coordinate is equal to the magnitude of the transverse force at a given point for all points that make up the beam. This is a fourth order ordinary differential equation, which we sometimes can solve with direct integration, but regardless of the method, solution of this fourth order integration will embody 4 integration constants, and therefore to fully solve this fourth order ODE, we need 4 boundary conditions. We also know that once and if we find or determine the transverse deflection field, we can differentiate it twice and multiply that result by the bending stiffness to obtain the moment field or the moment diagram. And since we know that the derivative of the moment plus the transverse shear force, internal force, is equal to 0 at all locations, that's the moment equilibrium equation, we can then obtain or rewrite that expression as follows. And again, for prismatic beams, the derivative of EI is 0, so that comes out of the bracket, and that tells us simply that the transverse shear force, the internal shear force, is merely the third derivative of that transverse deflection field that we have solved from the fourth order ODE times minus the bending stiffness gives us the shear force. So as you can see, if we can indeed solve the fourth order ODE and obtain V, the transverse deflection field, the little v, we can then obtain the moment diagram and the shear force diagram easily by evaluating second and third derivatives of that field. For any given well-defined beam problem, we're going to have 4 boundary conditions that we will need, and I'm giving you an example here. For example, if we're looking at a cantilever beam with fixed displacement and rotation on the left-hand side and with applied external moment and shear forces on the right-hand side, what are our boundary conditions? The boundary conditions on the left-hand side of this beam are kinematic type boundary conditions, and they're simple, easy to express. On the left side, V at 0 is equal to 0. as well as theta at 0 is equal to 0, but we know that the rotation of the neutral plane is nothing other than the first derivative of the transverse deflection field, so it's equivalent to prescribing v prime at 0 at that location to be 0. So here we have two boundary conditions on the left-hand side well defined. For the boundary conditions on the right-hand side, we have applied resultants, and these are not kinematic boundary conditions. These are so-called Neumann-type boundary conditions. And in this particular case, we are essentially, by prescribing a value for the shear force at position L, the length of the beam, we are, by the same token, prescribing a value for the third derivative of the transverse deflection field, because after all, we know Vy, the shear force, is equal to the bending stiffness times -1 times the third derivative of V. So therefore, it's equivalent to that prescription, and you can simply rewrite that prescription as V triple prime is being equal to minus VL over EIZZ. You have to pay attention to the sign conventions in here, and here this applied external shear force VL was a positive shear force. The fourth boundary condition there is a boundary condition that is actually implicitly applied on the second derivative of the transverse deflection field, because if the moment mz at L is equal to ml, the prescribed moment, then this means that EIZZ times the second derivative of the transverse deflection at L must be equal to that. Therefore, V double prime at L, it must be equal to ml over EI. So this concludes my basic overview of the mechanics of beams, and please make use of the other materials that I will be providing you as handouts, which will contain further theory as well as some worked examples on mechanics of beams.